Hey everyone, here we are solving a problem from RMO 2023. As you can see, this is a geometry problem. So first let's draw the diagram according to the question. So it says that let omega be a semicircle with AB as the bounding diameter. So first let's draw a circle. This is a circle and we will draw diameter AB. So basically our semicircle is the upper part. So basically this is our semicircle. This is the semicircle that the question is talking about. And CD be a variable chord of the semicircle of constant length. So what this means is that we will draw a semicircle chord, sorry, CD, and this is a constant length L. So basically we are taking a variable chord, which means that this could be the diameter or this could be the chord or this could be the chord, and all of them should have length L, and we could have named each of them CD. So let's first take one of the chords and focus on it. And it says that CD lie on the interior of arc AB. Of course, CD lies on the upper half of the arc. Let E be a point on the diameter AB such that CE and DE are equally inclined to AB. So this means that suppose this is the point A, and we have that CE and DE make equal angle, are equally inclined. So this means that this angle and this angle are same. We need to prove that the measure of angle CED is constant. So we need to prove that this angle, which is equal to 180 minus 2 alpha, is a constant. So basically this boils down to showing that alpha is a constant. If alpha is a constant, then of course 180 minus 2 alpha would also be a constant. So what we do is that, yeah, so both of these angles are alpha. And what we do is we construct the reflection of D over line AB. So suppose this is the reflection. Why we are doing this will be clear in a moment. And this is alpha. Yeah. So suppose we join E and D dash. We joined E and D dash. And notice that because it is a reflection, this is 90 degree, these two are equal. And suppose we name this base point X. So triangle EDX is congruent to triangle ED dash X. By, of course, by SAS, right angle side. This is the common side. Yeah, so this basically means is that this angle is also equal to alpha. So basically, because these are two vertically opposite angles, we can conclude that CED dash are collinear. So CED dash are collinear. So this is a straight line basically. If it joins these two lines, yeah, this is whole straight line. And notice that this is 90 minus alpha, and thus this is also 90 minus alpha because both the triangles are congruent. Now notice that uh, consider triangle CDD dash. If we consider triangle CDD dash, then by sine law, what does the sine law say? It says that L upon sine of 90 minus alpha is equal to twice of R, where R is the radius of the circumscribing circle. So what this means is that L by 2R equal to cos alpha. Yeah, L by 2R is cos alpha, and we can say that alpha is equal to cos inverse L by 2R. What this basically means is that alpha can be determined wholly by L and 2R, and both of them are constant. So we can basically say that alpha is a constant. So this proves the first part of the problem. Now we have to prove that circumcircle of triangle CED passes through a fixed point. So if you like make some observation, draw some circumcircles, one particular point of interest you will notice is the center of the circle. Suppose we consider the center of the circle O. First, let us remove all this. points. For clarity, if we take the center of the circle O, then basically these 4 points look like cyclic. And if we prove that CDEO is cyclic, CDOE is cyclic, suppose we prove this, then we are basically done because we haven't assumed anything special about this chord CD. So O would be cyclic with any other chord. So if we take any other chord, then also these 4 points would become concyclic. So this would solve the problem. So let's focus our attention to proving that C, D, O, E are cyclic. So to do that, what we can do is, suppose we connect, wait, this would not be O. Yeah. So suppose this point is O. And what we do is we connect C and D to O. We connect C and D to O. And notice that this angle is alpha, as we have, sorry, this angle is, say this angle to be, suppose we say this is X. And this X proves that this is also X because both triangles are congruent. And this X already makes that this angle is 2X because angle at center, this is a very well known property, angle at center equal to 2 times of angle at arc. So basically this proves that this angle is 2x, and if angle COD is 2x, this is what we get, COD is 2x. And also notice that because angle CED equal to angle EDT dash plus angle ED dash D. So what this basically means is that this red angle here is equal to sum of these two angles. This is pretty clear because opposite angles is equal to sum of inside angles, and this is also equal to 2x then. So we get that this is equal to 2x, and thus this is also equal to 2x, and by angle in the same segment theorem, CEOD are cyclic, which basically means that CDOE is cyclic. So we have shown that CDOE is cyclic. So O passes through the circumcircle of CED. This basically means that O passes through the circumcircle of any such CDOE, and we have shown that circumcircle of CED passes through a fixed point because O doesn't change as CD changes. If CD changes like this or like this, then O doesn't change. Hence, we have shown that CED passes through a fixed point. This was the solution. Thanks.